Good morning, good afternoon, and good evening once again, everyone. Welcome to the RTDS Technologies User Spotlight Series. This is week number 9, and my name is Katie Sidwell, a simulation specialist with RTDS Technologies, and I am your host and moderator today to take you through 2 more exciting user presentations featuring novel applications of the RTDS simulator. I can't believe it's already been 9 weeks of this event, and we only have 2 weeks to go after today. If you haven't looked at those session descriptions, I encourage you to take a look. I think they're going to be particularly exciting, so please feel free to sign up for those if you haven't yet. If it's your first time joining us, then welcome. If you've been with us for part of the journey or the whole journey so far, welcome back, and thanks for sticking with us. I just want to remind everyone, we encourage you to ask questions all throughout the presentations today. The presenters will be online and ready to answer your questions as they come in, and those can be submitted via text in the Q&A widget. So you should see that near the top left corner of your webinar platform, or you can access it by clicking the Q&A icon in the icons toolbar near the bottom. If you are joining us on demand today, which means you're accessing the content after the webinar has already happened live, you can still ask your questions, and those questions in the Q&A window will be responded to via email by our presenters. As always, I also want to encourage everyone to say hello in the chat window. Please feel free to introduce yourself. Let us know where you're joining us from. I wish we could be together for the users group meeting in person, but unfortunately that wasn't possible this year, so this is the next best thing. You can also access the slides for today's presentations. They're available in the Handouts widget, which should be in the bottom left-hand corner of your screen, or you can click on the Handouts icon. It looks like a piece of paper in the icons toolbar. Just before we get started, I also want to make you aware of some upcoming events that RTDS Technologies is presenting in or participating in. One is the ISGT conference. That's the Innovative Smart Grid Technologies conference out of Europe. And RTDS Technologies is hosting a panel session on Wednesday, October 28th at 6 p.m. Central European Standard Time. And that panel session will feature presentations from a few different users regarding smart grid testing with the RTDS simulator. And that's going to include a new demo from RTDS Technologies of HIL testing and intelligent recloser. So if you are already registered for the conference, please join us for that session. And if you're not and you're interested in the session, you may want to visit the conference website to learn more. Lastly, if you speak Spanish or Portuguese, we are participating in a microgrids online course. Our session is on November 4th, and it's a really good 1-hour plus crash course on microgrid testing with the RTDS simulator. So if that sounds like something you're interested in, please drop me an email at katie@rtds.com for more information. Now, without further ado, I'm going to go ahead and introduce our first presenter. Yeong Kim received his bachelor degree from Myongi University, Korea in 2019. He is currently in his master's course for electrical engineering at Myongi University. His main research interests are power system protection and power system transient simulation. Please welcome Yeong Kim with his presentation, Development of a Current Transformer Model with Saturation Characteristics.
Thank you for the introduction. Hello everyone. Today I would like to present you development of a current transformer model with saturation characteristics. My contents are divided into 4 parts. The first part is introduction of the current transformer. Second part is development of a CT user-defined model, the purpose of UDM, equivalent circuit, and applied method are explained in this part. Third part is simulation studies. First step is to verify the CT UDM by applying open circuit test. Second step is to apply CT UDM to the power system. Final part is conclusions. Introduction. The protective relay performs protection by receiving current signal from the current transformer. Therefore, CT should provide the relay with the correct current value in the event of fault and the normal state of the power system. However, saturation due to the magnetic properties of CT results in distorted signal, which leads to maloperation or operating time delay of relay. Many utilities, including Capco, use real-time simulators such as RTDS to perform dynamic tests of relays on CT saturation. Some CT saturation countermeasure algorithms use nonlinear saturation characteristic curve of CT to cope with these problems. Therefore, a model that can simulate nonlinear saturation characteristics is required. However, when Vrms Irms excitation curve is applied to the RTDS CT model, the curve obtained from each simulation is a bit different from the applied Vrms Irms data. Therefore, this presentation describes the already suggested method for developing CT UDM that correctly reflects the input data. I made reference to the unmodeling iron core nonlinearities and nonlinear and time-varying elements in digital simulation of electromagnetic transients to develop the CT UDM. The developed CT UDM was verified by open circuit tests, and its performance was tested in the power system modeled in RSCAD. The purpose is to develop a model that accurately reflects the Vrms Irms data entered. The following figure shows the relationship between the exciting voltage and exciting current measured by the CT manufacturer in open circuit test for C800 CT. This data is the exciting current for the sinusoidal input voltage, and this data includes core loss and secondary winding resistance and leakage reactance. In the general CT equivalent circuit, secondary winding resistance and leakage reactance can be included in the burden impedance. And in the case of current transformer for protection, if CT is saturated, the core loss is less important than saturation characteristic, so the core loss is not to be considered in here. Therefore, I would like to consider a simple circuit by ignoring core loss, secondary winding resistance, and leakage reactance, like this. Then the data from the 10 points obtained from the exciting curve is used only to reflect the magnetizing inductance branch's nonlinear properties. The reason for using 10 points RMS voltage and RMS current is that the RTDS CT model also uses 10 points data. As already mentioned, the voltage obtained from the open circuit test is a sinusoidal wave, but the current is not a sinusoidal wave. The RMS value measured from the non-sinusoidal current must be converted to peak value for modeling. I used the 10-point RMS voltage and current data for the modeling of the magnetizing inductance branch, but here I will explain as an example how to calculate the peak flux and current curve of the magnetizing inductance branch using 3-point RMS voltage and current data. In the step 1, Vrms Irms data is computed as peak values for voltage and current, and in the step 2, peak values of voltage are computed as peak value for flux. Here is the first step. According to the open circuit test, input voltage is a sinusoidal wave. So, obtaining the point from V1 to Vk on the vertical axis is simply a rescaling procedure from RMS to peak values. For the first linear segment in Vi curve, the calculation of the peak current I1 on the horizontal axis is straightforward. Because first point of RMS voltage and RMS current is in the linear segment, so first point of the peak current is obtained by multiplying RMS value by square root 2. Now the peak current at the remaining points except the first point can be calculated. Because of the symmetry of the VI curve with respect to the origin, it is sufficient to observe quarter-hour cycle. Assuming that the input voltage Vk is equal to Vk sin theta, then for the following segment, K is greater than or equal to 2, the peak current Ik is obtained by evaluating RMS current value for each segment K. Here we use the definition of the RMS value. In this equation, only the last segment of Rk is unknown. So Rk is easily computed and peak current Ik is calculated from this equation. This computation is done segment by segment, starting with the second point of RMS current value and ending with the last point of RMS current value. Whenever a last point of peak current has been found for the horizontal axis. In this way, RMS data can be converted to peak values no matter how many data points there are. As an additional example, Circle 1 shows the current waveform when the V1 voltage is applied, and Circle 2 and Circle 3 show the current waveform when the voltage V2 and V3 are applied respectively. In step 2, VI curve is computed as the flux psi curve. The left-hand curve is the symmetry of the calculated peak voltage and current values to their origin. The non-linearity on the left curve is the voltage as a function of current. This means nonlinear resistance. Actually, we need the nonlinear inductance curve. The nonlinearity of the inductance is usually expressed flux as a function of current. According to the relationship of voltage and flux, flux can be expressed with the voltage. And with the trapezoidal rule of integration, finally we can obtain this equation in the form of voltage and current. This relationship between voltage and current in this equation can be applied from the peak voltage and current relation obtained previously. Now I will explain the network solution method. For the linear networks that do not include nonlinear elements, solutions can be easily found through the nodal equation. With only one nonlinear element in the network, the solution can be kept essentially linear by confining the nonlinear algorithm to the branch with the nonlinear element. In this case, compensation method can be applied, whereby the nonlinear element is excluded from the network and replaced by a current source like this figure. The total network solution VKM is then equal to VKM linear found with the nonlinear branch omitted plus the contribution produced by the nonlinear branch. Thevenin resistance in this equation is the resistance of the network without nonlinear branch connected between node K and M. The solution process in each time step is as follows. First, compute node voltage without nonlinear element. Second, solve the two scalar equations, network equation and nonlinear equation, simultaneously for current source IKM. IKM is the solution. Finally, the final voltage solution can be obtained from superimposing the response to the current source IKM. The first solution process is to compute node voltage without nonlinear elements. According to the Domel's method, inductors and capacitors are replaced by resistor and current source in parallel, and their integration into a nodal conductance matrix and injected current vector, respectively, to find the solution for the system. There is an inductor in proposed CT equivalent circuit, which is replaced by a resistor and current source like this. After computing node voltage without nonlinear element, the total network solution VKM is then equal to the value VKM linear found with the nonlinear branch omitted and plus the contribution produced by the nonlinear branch. This is the network equation. The nonlinear equation is the relationship of voltage and current obtained previously. So, we solve the two scalar equation, network equation and nonlinear equation simultaneously for current IKM. Then, find the final voltage solution by superimposing the response to the current source IKM from network equation. This is how to compute a linear network with nonlinear elements in a digital computing environment. The two modeling techniques described before were applied to CT-UDM under RSKD C-Builder environment. The left side figure is the appearance of the model, and the right side shows model parameters. 10 points of RMS voltage and current data can be entered to the model. It is also possible to monitor CT secondary current, burden current, magnetizing branch current, flux and burden voltage. Next part is simulation studies. CT-UDM and RTDS CT model are compared together in performance verification. 10 points of VRMS IRMS data are used as the reference data in model verification, and they are also used as input for those two models. In order to compare with the input data, a sinusoidal voltage should be applied to measure the current flowing in magnetizing inductance branch, which is similar to that CT manufacturer measures the relationship between secondary exciting voltage and the exciting current. However, because CT-UDM and RTDS CT model operate based on current source, so we cannot apply voltage source to these two models. If the burden is set to a value close to 0, the input current will almost flow to the burden as if it was a short circuit. This current generates a voltage almost identical to the sinusoidal wave with burden. When this generated voltage was applied to magnetizing inductance branch, which connected in parallel to the burden, the current flow into this branch can be measured. In fact, there are two ways to simulate CT saturation in RTDS. One is using RTDS CT model, and the other is constructing a CT equivalent circuit using saturable reactor model. As mentioned earlier, VRMS IRMS 10 points from exciting curve will be used. VRMS IRMS data is one of the input saturation characteristic data types of the RTDS CT model. We can input 10 points of data to this model, so RTDS CT model will be evaluated with CT-UDM. In order to verify both models under the same circuit conditions, Core loss, secondary winding resistance, and leakage reactance are set to 0. By simulating RTDS CT model under these conditions, the hysteresis loop without area can be monitored, which means there is no core loss. This is the result. The last point of the VRMS-I-RMS used in both model is the RMS current of 9.98 ampere at 850 RMS volts. The left and right figure are the results of CT-UDM and the RTDS CT model respectively. The figure below the circuit shows the burden voltage and the magnetizing inductance branch current. The meters shown on the right side of the circuit are RMS voltage and current values, and the result of CT-UDM yield almost the same result with last point of input data. On the other hand, the RTDS CT model shows a bit different result from the input data. On the middle, the simulation result is shown using a script to increase the RMS burden voltage from 0 to 850 volts with a gap of 5 volts. The black line is the result of CT-UDM, the red line is the result of the RTDS CT model, and the blue line is the reference that is input data. If the same data were applied to both models, CT-UDM would give the same like the input data curve, but the RTDS CT model is a bit different from input data. Compared with CT-UDM, the result from RTDS CT model is saturated rapidly when it starts saturating. In the RTDS CT model, if the saturation characteristic data is entered as VRMS, I-RMS values, these values are converted to BH values. I think this BH conversion process or other techniques such as curve fitting technique cause these differences. Then I applied both models to the power system. The 154 kV system on the left and the 23 kV system on the right are connected to transmission line and transformers. Relaying point is the point expressed in the blue circle, and fourth point is the red point. This is the case of single line to ground fault, which is at 10% transmission line from the relaying point. The resistive burden of 8 ohms was applied to both models. From the upper right figure, primary current, results of CT-UDM, and RTDS CT model are shown in order. The black line is the burden current, and the red line is magnetizing inductance branch current. As mentioned earlier, the RTDS CT model is rapidly saturated when saturation begins. The resistive burden and reactive burden are applied to both models. For the conditions are the same with the previous case, and similar with previous results, our RTDS CT model is rapidly saturated than CT-UDM. Conclusions. To sum up, when I entered VRMS I-RMS data to the RTDS CT model, its simulation research was a bit different from the input data. Therefore, CT-UDM, which accurately reflects input data, was developed based on already suggested method. Simple circuit was obtained by ignoring co-loss, secondary winding resistance, and leakage reactance from the general city equivalent circuit. This CTUDM was verified by open circuit test research and finally applied to the power system, which is modeled in RSCAD. In future, I will test the performance of the CT saturation detection and compensation algorithm with a distorted signal obtained from the CTUDM. In addition, I will implement the effect of residual flux by considering coal loss in the model. The references are as follows. Thank you for your attention.
Thank you so much for that presentation, Yeong, and thanks to our audience for your questions so far. Please keep them coming for our second presenter. I'm pleased to introduce Aleksandr Zelenin. Aleksandr Zelenin graduated from Peter the Great St. Petersburg Polytechnic University in 2012 with a degree in relay protection and automation of power systems. His final work was devoted to the issues of constructing model software for real-time operation. While studying at the university, Aleksandr got a job at the Research Institute of DC, today Joint Stock Company Scientific and Technical Center of Unified Power Systems, JSC STC UPS. He was engaged in the physical modeling of power systems for the purpose of checking and setting automatic voltage regulators and power system stabilizers. JSC STC UPS got the RTDS in 2013. Aleksandr started to work with the simulator. The following work on RTDS has been carried out with Aleksandr's participation: study of AVR and PSS, phasor measurement units, phasor data concentrators, emergency control devices, automatic load shedding, group station control. Today, Aleksandr Zelenin is a senior researcher of the RTDS laboratory. Please welcome Aleksandr Zelenin with his presentation, Automatic Voltage Regulators and Power System Stabilizers Digital Model Verification Experience Using Frequency Responses Obtained by RTDS.
Good afternoon, colleagues. My name is Aleksandr Zelenin. Today I'm going to tell you about our RTDS use experience in field of obtaining automatic voltage regulators and power system stabilizers frequency responses. These frequency responses or body diagrams are obtained from natural devices via specialized procedure. In our company, we carry out research and testing of our using different approaches, such as digital modeling in specialized software, physical modeling, and mathematical modeling in RTDS. We carry out experiments for frequency-aware and PSS responses in order to improve their quality work in Russian power grid. The correct representation of these devices in the power system digital models is one aim of our work. We test regulators from Russian developers and from foreign developers. And of course, regulators which was built with regards to IEEE standards. In this presentation, we will focus on regulators based on foreign IEEE structure. Here are some photos from our research laboratory with natural awares. So main reasons why we need to obtain aware frequency responses are following. After developers have chosen the appropriate structure from standards, they become to develop measurement algorithm and input digital processing of aware. So they choosing this part and from standard and develop their measurement algorithm and digital processing with part. However, these developers give our digital models to research studies, but their digital aware models do not include measurement algorithm and specifications. So models are incomplete. So in our words, they give us this part and do not include to model this part. The second reason is caused by using discrete equations implementation. Sometimes discretizations made by developers is not accurate. This leads to mismatch between the real device and original models in equations. Also, the presence of software error caused by change in sampling frequency of calculation function can also lead inaccuracy and error models. The test procedure for frequency responses obtained was developed in 2013. We talked about it in user meeting in Copenhagen where shared the first results. It is important to note that use of developed test bed solves several research problems. It is important to mention there is no need to any specialized preparation because the complete limitation of real-life connection is performed. The AVR operates in closed-loop system. So is a closed-loop system with allowing in function properly, including integrator blocks element. It is known that integrator block elements without feedback sometimes do not allow carry out experiments because this block quickly reach the limits. By modeling the voltage amplitude or the frequency and power system and generator angle, it is possible to obtain the frequency responses for each of control channels. So here is a closed loop system. Here is a scheme connect between RTDS interface and real aware and input signals in the this test procedure. This slide shows one of the typical AVR instructions, which includes the following elements: PID voltage regulator, usual PID voltage regulator, and PSS with two channels as inputs: rotor frequency, which normally calculated in the frequency of the voltage, and active power channel. Usual approaches require the procedure to get frequency responses for only one channel work. So you should, with usual approach, you should to use only one channel to switch on, only this, or only this, or only this, and this, but there is a problem because not all AVRs allow to switch off main voltage channel. So this channel can't be switched off in some device. Developed test procedure accounts for this fact. It can used while several control channel works simultaneously. So this procedure gives us possibility to get frequency response while several channels works. For example, voltage channel, which can't be switched off, and for example, with part of PSS. So main model features are described on this slide. The model is designed in such way its influence to the results of the experiment is minimal. For instance, there is no saturation present in the model, and parameters of synchronous generators are set in way to remove their influences. Let me tell you about how initial model verification are performed. First, we get frequency responses from real-time regulators. Then we compare them to ones we obtained from mathematical model that is sent to us by a developer. Let's call it a manufacturer model. This manufacturer model is then corrected together with based on experiment results and aware documentation developed and developer communication. But by this way, we add model elements which taken into account. The error at each point is estimated in according to the formula on the slide. As you see, it considers both the amplitude difference and the phase difference. Amplitude difference and the phase difference. And main role in aware tuning plays phase response. So phase model errors will make big contribution to total error. So main part of this error is created by this element. We consider the model to be accurate of the error does not exceed 10% at any given point. In this slide, you can see some results of applying our method for several voltage regulators. In left part of table, you can see the results comparing the initial manufacturer models with experiment frequency responses. So here's the experiment. Here is a manufacturer model results. As you can see, uncounted meter models and some digital processing leads to higher error with increase of oscillation frequency. So, as you see, with but the diagram have errors which is increasing with increasing frequency. So, after correction, which we made by experiment results and developer communication, we've got the same responses, and our error is become very low, less than 10%. Similar results we can obtain for our channel, for example, for frequency control channel. Here is a response from model of manufacturer. Here is the responses from experiment results, and here is the error of the model is the initial manufacturer model. So after correction, which is includes digital processing and meter models, we get error which is less than 10%. For example, before correction it was 30%, and now it is at 10%. The same results for channel of active power. So it's a manufacturer model, experiment results, error, and these results after correction. So in our experience, the initial manufacturer models of AVR and PSS remain correct up to frequency 0.5 or 1 Hertz. So in this table, you can see the frequency values in which initial manufacturer models are correct. So for example, for 4 regulators, for regulator 1, 2, 3, in the channel with the channel voltage, frequency, active power, and for example excitation current. And after correction, we got good models for these devices which correct in all frequency range from 0 to 10 Hertz. So these results does not meet requirements of IEEE standards, which requires that frequency limit is should be 2 or 3 Hertz. But after correction, it became okay, and frequency range of AVR models is become with in this value. Zooming out, I'd like to mention that despite many years of experiments that Russian and foreign manufacturers have, the quality for information they provide about their own device is not always satisfactory. This fact can lead to power system digital modeling errors. This is why it's very important to perform experimental device verification. That is exactly what we do in our research center. In addition to AVR, we are engaged in research and experiments with our power system control devices. Some of them are named in the slide. So here's the contacts which you can write to me, and thank you for attention. I'd like to answer your question if you got. Thank you.
All right. Thank you, everyone, for your attention today. And thank you to our two presenters, Yeong and Aleksandr, for those great presentations. Again, I put this in the chat, but I'm really sorry that those slides on the second presentation were displaying very small. That is my bad. So if you want to download those slides, they're just in the handouts area, and you can view them at a higher resolution. But before we close today, let's get on to discussing a few questions. The first question is for Yeong. Is it difficult to consider secondary winding resistance or leakage reactance in your user-defined CT model?
Can you hear me?
Yes, yeah, you sound clear.
Yeah, it is simple to consider secondary winding resistance and leakage reactance in user-defined model. The additional elements will be linear elements. Therefore, it is only necessary to modify the conductance matrix of the nodal equation required for linear network solutions. If you are using C-class current transformer like me, you can ignore the leakage reactance because of the tight windings. And also you can find the details of the current transformer types from the IEEE or the IEC standard.
Great, thank you. Another question for you. Have you applied any similar work to non-instrument transformer models, to conventional transformer models in RSCAD?
I never tried about similar model like current transformer or voltage transformer, but I have experience in making models that performs distance relay or current differential relay function to protect transmission line.
Great, thank you. Let's move over to a couple of questions for Aleksandr. Aleksandr, what was the original motivation for doing this work to characterize the AVR and the PSS frequency response?
Do you hear me? We need to do AVR
Yes, you
and
sound good.
PSS tuning in digital power system modeling. So when we should to do the tuning, we should to have a very good AVR and PSS models, because the results depends from accuracy of these characteristics. In our power system, we have long lines, which leads us to make very high values of gain in PSS and stabilizing channels. So without good characteristics, we can get high frequency oscillations if we will increase gains without clear frequency responses of AVR. So
Thank
that's
you.
why.
Great, thank you. Aleksandr, do you want to go more into the reason for being interested in the response of the excitation controls beyond a hertz? For example, maybe for torsional issues, subsynchronous resonance, you need a higher frequency accuracy?
1 second. We need to get wall frequency range because in some transfer functions there are poles and zeros is very close to zero frequency. For example, in washout in PSS. So to get clear model, we need to get a wall frequency range. So with frequency beyond 1 hertz.
Great, thank you. Let's go to a question for Yeong. On slide 20, it looks like your model is using piecewise linear approximation to the curve, whereas the RTDS model uses the least squares method to approximate the smooth curve to the input data. Have you tried the RTDS model with curve fitting turned off so that it does something similar to your model?
Yeah, I have tested both of them already, but you know that if VIRMS data is used for the RTDS city model, BH curve fitting algorithm should be selected. There are two options on the RTDS city model. The first one is least square method, and the second one is fixed line slope method. I tested both options, and I found similar results to the presentation.
Great, thank you. Let's go back to a question for Aleksandr. What was the result of the characterization of the AVR and PSS used in other simulation programs, for example, RMS-based or transient stability analysis-based programs?
So these characteristics which we can get from our programs, it's mathematical characteristics which sometimes do not include AVR and PSS devices real implementation. So the main reasons to make it in RTDS with real device to get a real implementation of mathematical models, because the main problem here is step from going from mathematical model to real device. Sometimes developers and manufacturers do it is not so clear. So that's why we're doing it in real devices.
Right, thank you. I think this next question will be our last one before we wrap up, and it is for Aleksandr. What do you think is the main reason why the initial mathematical models cannot be used? Is it due to the change in AVR parameters because of aging, or is it incorrect measurement in the parameters?
The main reason because manufacturers do not include digital processing to their models. They give us IEEE standard model without digital processing, which have their own characteristic and responses. Without this part, model is not so clear, and as you saw in presentation, in high frequency, it became is not clear. That's why.
Great. Thank you, Aleksandr. I think that wraps up all of our questions for today. Thank you so much to our audience for attending and engaging. And a special thank you to both of our presenters attending from Russia and South Korea today. Thanks for being with us in your various time zones. And I hope to see everyone again for the next 2 weeks. Please drop any questions in the Q&A or in the chat. And thank you for joining us. See you next time.